Hello, everyone. Thank you for attending my talk today. Today we will, as Valuenex is a company who works in the natural language processing space, especially our bread and butter building cluster maps of patents and research papers, walk you through the sort of global quantum computing landscape through analysis of the patents and research papers that have been filed. Now, you may think, well, as a software engineer in the NLP space, kind of presenting about quantum computing landscape, well, towards the end, we'll have some thoughts as to how we think in our algorithms and calculations we can include some of these technologies. But more importantly, we think to truly understand a landscape and to truly understand an industry, you really should start looking at patents and start looking at the research papers, the density of which patents and research papers are being filed to understand what everybody's working on and to understand the progression of technologies that are being developed. So a little bit about Valuenex. We're actually a Japanese company. We're on a public company in Japan. And we work with some of the bigger clients in the sort of Japanese landscape. And more importantly, I think we work with a lot of R&D departments. The reason why they come to us for patent landscaping and for research paper landscaping is because I think we have attention to detail when it comes to creating some of these landscape maps. Part of it is that instead of, for example, using just a title and the abstract of a patent, we would go ahead and we will weigh different sections of a patent as we go through and create these cluster maps. As a result, what we really see here is this is our Valuenex radar. What we do have is different densities shown in a sort of heat map style where we can visualize patents and research papers as we go along and we understand the quantum computing landscape. To explain how you kind of understand our cluster map here, what we have in the is a sort of a heat map style where the red areas are dense areas of high density, hence they're called major areas. Growing areas are areas of higher density where the increase in velocity of the density of that area is faster than any other area. One of the cooler parts of our radar is the sparse area, which is an area of low density surrounded by high density with the potential of the higher density areas flowing into the lower densities. So as you map out the entire landscape of a quantum computing sort of space, what you really get to see is the densities of patents and research papers in different areas and different technologies within the industry shift and change over time. And so this is where we're going to present to you how we think could offer a different perspective in terms of how you can understand the quantum computing space. So we're going to split this presentation into two parts. The first part is going to be the patent analysis, and then the second part is going to be the research paper analysis. So looking at the patent analysis, what we really want to understand are the trends and opportunities in quantum computing, what are the key focuses in quantum computing, and what is the competitive landscape in quantum computing. To begin, this is what we present every year, so it's a continuation of what we've presented at Q2B is the US patents. In this case, we've taken a sample of many, many more patents, but we've clustered it down to look at 1,425 clusters across 5,700 patents. And the time range of these patents that we're looking at in the quantum computing space is from 2000 to 2024. Just to recap on what we've mentioned previously, this is what we presented last year. As you can see on the sort of very left-hand side is a major cluster, and that's the hardware cluster. Actually, in 2023, what we noticed, especially within the US patent landscape, is that the software was aggressively being sort of explored in terms of a patents, especially on the application side. And what that did was within 1 year, it stretched the sort of software landscape all the way out. And it created a ridge in the middle, this sort of empty area of low density. Now, where the story and the thesis and the explanation that we had was, and you can possibly see, especially at this conference, where a lot of the players, not only a lot of players are originally focusing on the hardware side of things, were either looking for M&A opportunities or looking for opportunities in-house in terms of R&D to expand into a full stack capabilities. And they were hiring software engineers to build the sort of software that took it above just low-level assembly code and allowed you, to a certain extent, all the way up to the application layer where you can launch Jupyter notebooks and do benchmarking and so on and so forth. So a lot of patents were filed like this. At last year's conference, we did mention that our thinking is that because the expansion was so aggressive, that it would sort of come back towards the middle, towards some of the hotter topics. And essentially, this is what we're going to show you guys this year as well. So indeed, this year, we see actually a much more dramatic shift than we expected. So 2000, it moved out to 2023, that 1 year, all the way into the software side. And we did see quite a bit of a reversal in 2024 as it moved back in. And now I'm going to walk you through the sort of more detailed radar from 2024. So on the right side, what you have here is a sort of course, some of the topics, not all of the topics, but some of the more traditional topics that we talked about in the hardware space, from the quantum annealers to topological qubits to so on and so forth. And then on the sort of left side, what we have is the software applications. And Doug touched on, of course, quantum error correction and so on and so forth with noise reduction and more. And on the very left side, we have some of the application layers. So we have the machine learning algorithms, models and algorithms, and actually simulations down here. So this year, just starting from the left and moving back towards the right, this year on the left, we actually noticed a lot more in terms of simulations. I guess because there's much more in terms of software, people are exploring more in terms of simulations. Whether or not this is effective, whether or not it achieves the best results, that's a separate question. But at the very least, you see a lot more patents that are actually being filed in the simulation space. Same with machine learning models and algorithms. It was very hot, but actually we'll explore more of that in the research paper side later on. And just going off of the last presentation, as Doug mentioned, quantum error correction. That sort of, if you still remember from our last year's map, we had that sort of blank space in the middle of low density. Now we're seeing more and more patents come back towards that side where quantum error correction is a definite focus. Especially, we noticed in terms of patents filed for some of our hardware players. I think the idea is that they're trying to build that into the hardware layer as well, almost as a sort of low-level software, and then offer that hardware back out so that people can tap into it with the sort of error correction potentially already somewhat built into that sort of hardware offering that they already have. But on the software side, of course, there's a lot of third-party quantum error correction software as well that are being worked on. So one thing about Valuenex is we're also able to isolate by individual companies. So in the case that anybody in the audience has the need or want to sort of see where your patent portfolio lies relative to everybody else, or if you're an investor looking to invest into the quantum computing space and you want to see how your portfolio stacks up against the rest of the industry, this is something we can do for you. I'm just going to quickly showcase, what that really looks like for us. So IBM, this is what we have for the patents that they filed. Microsoft is, not really too popular in the traditional hardware space. They tend to look at topological qubits, so on and so forth. Of course, both of them having a very sort of big focus on quantum error correction. And Intel, of course, with the fabrication and so on and so forth. But of course, looking at US is very singular. We want to expand it to see if we can learn more when we take a look at Europe, Japan, and have all the other players included as well. So we expanded the data set, and of course, we sampled it back down to about 8,000 patent applications across 1,263 clusters with the same time range from 2000 to 2024. As almost a control, we've left the US patents in there so that we can also understand where the rest of the world is relative to what the US is doing. So similarly, we have a new map here. On the very left side is the hardware applications, hardware, and then on the right is the applications. In the middle, we kind of have that software side. As you can see, when you bring in the European players and especially more of the Japanese players, the hardware side becomes much more concentrated. And as you can see, there's of course quantum photonics that gets brought back in. There's more memory devices, optical components, sensing, and some of the sort of more direct components are where a lot of the patents are being filed. When you look at something like quantum error correction and noise reduction and actually that space, when you bring the sort of global landscape back together, actually it starts looking much more sparse. And I think that's one of the big differentiators when we compare it to the US patent landscape. And again, this time actually the trend line is much more simple. I think as a sort of global push, there isn't as dramatic of a shift as we've seen in 2023 with the US side. And partly that as we have conversations and we go around, it seems like a lot of those decisions are investor driven as well, where we notice that hardware players, there might have been some investment pressure, especially in the US side, to sort of start building out full stack applications and trying to find more sticky customers, which may or may not be the right approach and also has its pros and cons, but that's the trend that we're kind of seeing. So now isolating by country, what really interests us is to be able to see the patents that are filed by corporations more or less roughly that represent the country. Of course, again, this is a sample space. Please come talk to me offline and we can look together at the sort of entirety of the sort of space, because it's much easier to look at our radar in our website where it's live and you can scroll and zoom in and zoom out and filter by different companies rather than sort of presented in a static form such as this. But in terms of Japanese space, once again, very heavy on the hardware side, and that's more or less where most of the activity is going on. On the European side, it's slightly more balanced with focus on quantum noise reduction approximation with a bit more on the error correction. But more or less speaking, still sort of what you can see is that sort of hardware focus as well. And I think this is just further proves the point that at such an early stage, a lot of collaboration, especially between countries, between ecosystems, really does help. So for example, last time in our presentation, we did a network analysis where our partner provided the data from Crunchbase, and we took the investors, founders, and advisors, and so on and so forth, and we put them together and we created this map. We actually identified a couple key nodes, such as the European Innovation Council, Creative Destruction Network, labs, and if you brought some of these players together, there's actually a lot of synergy in terms of where the collaborations can lie. And I think this is true between, for example, the Japanese case and the European case as well. Of course, patents have a lag, and they don't always show you the latest products and technologies and developments that are out there. So we would always recommend to look at research papers as well, because some of the newer concepts are usually covered by research papers. So the source that we use is Scopus, and we pulled a much larger set of research papers, and we kind of sampled it back down to about 8,696. Very similar time range from 2000 to 2024. So funny enough, for research papers, of course, there's that middle section in yellow, which is some of the more theoretical concepts and experiments and phenomena, quantum phenomena. But at the same time, we have a very sort of similar faces that we always like to see, the sort of purple in the applications and the red on the left side on the hardware itself. One thing about research papers that immediately differentiates in terms of patents is actually on the application side. So you actually see this new area on quantum cryptography and security. It's not that there's no patents filed there, it's just research has always had a heavy focus on this space. And there's a lot of papers, technical and non-technical, kind of published in this area. The quantum algorithms, optimization algorithms, and the machine learning models and algorithms is also very, very heavy focus on the research paper side. And we're going to show you in the next slide how in 2023, that's actually one of the biggest drivers of the research papers that are being published. And that goes hand in hand with the sort of hype in AI. But I won't spoil the sort of results of 2024 in that space, and I'll let you guys get to that later on. But same thing here in terms of the error correction, noise reduction approximation. There's a lot going on in that space, especially in the error correction space. As Doug mentioned, with sort of these new algorithms that come out, there's a lot that is driven here in terms of quantum error correction. And actually, one of my really close friends who's doing a third-year PhD, he is now specializing in the quantum error correction space as well. And on the very left side, you have some of the more traditional topics, of course, in the quantum computing hardware space. But we were quite surprised that the topological quantum computing generated such a heat map in terms of area as well. And of course, quantum dots and spin, and from a academia standpoint, is a very hot topic. And photonics is, of course, always a very big concentration in academia as well. And it's sort of sparse, but in the middle are some of these concepts that are theoretical, but they get covered. And that includes quantum sampling, quantum complexity information theory, quantum mechanics and Hamiltonian, and quantum correlations and discord. So in terms of the trend, I think it sort of reflects a little bit of, and it stays a bit closer towards the US trend of the patents, where there is more of aggressive sort of transition downwards in the software space, into the software space and application space. And I think this just simply speaks in terms of how the industry is looking at these full stack applications, software applications, and things of that sort, that as the hardware progresses, these are just natural progressions of what people intend on building on top of that. So this is going back a year to 2023, and I think what really interests us in 2023 was the fact that machine learning models and algorithms, especially relating to quantum computers, was such a hot space. And I think everybody knows in 2023 this was a big area with a lot of grants and a lot of research was directed into this area. But what was really interesting, actually, is that if we flip to 2024, the machine learning models and algorithms actually scaled back. Of course, we're only at this point in July, but rest assured, when we did the Santa Clara and the other Tokyo sort of Q2B presentations, we did notice that it was at this point in the year, it was a much hotter heat map. In terms of the machine learning models and algorithms. So, on one hand, of course, this is the hottest topic, and it still is. But on the other hand, it might be that our thinking is that it's potentially that people start recognizing that you can't just throw a blanket machine learning algorithm into the quantum computing space, that it might be the sort of hybrid approach where people start realizing that different parts of your algorithm and different parts of your optimization process can be used in terms of different specialized quantum computers, or more so just with your classical computers that can do better. And I think this is, at Valuenex, this is something that we're thinking about as well, because when we do create this sort of visualization, it is very computing intensive. And we also think about how right now, where we calculate everything together at once, as we split up these different parts of calculations that help us optimize our process, which parts should be done with classical computing and which parts should be done with quantum computers. And I think when we sort of think of it in that sense, it might be very similar in terms of how people are understanding machine learning relative to quantum computing, that it's not just a blanket sort of machine learning algorithms that work with quantum computers, is that there's a sort of different stages and steps where different models or different parts of the optimization process, some of them work with classical computing, some of them work with quantum computers, and different hardware have different specializations for different purposes. And so maybe that's also the reason why the research papers for that space come and get spread back out. So just to drive a conclusion, thank you everybody for listening. I think sort of coming back towards Valuenex, and sorry to talk a little bit more about Valuenex and a little less about quantum computing, is that we're a company who offers this service, and we offer this service across different landscapes and different industries. We work very heavily in the automotive industry. We work very heavily with insurance and R&D departments and buy-side investment. But yes, hopefully this gives you a different perspective through the patents and research papers on quantum computing. And thank you everybody for listening.
Thank you. There is 1 minute on the clock, so if anyone has any questions, please ask now.
Yes, please.
When you analyze patents, do you analyze when a patent is applied for or when it's issued?
So in this case, we go through all the applications and the patents themselves. And as I said, we try to take a slightly different approach where instead of going for a lot of titles and abstracts, we try to go through all the patents as well, the actual contents in the patents, and weigh that against each other. And we look for the applications. And US PTO, for example, we take the applications plus everything else. Yep.
Okay.
Yep.
Any other questions? ご質問ございますか？大丈夫でしょうか？はい。Thank you, Mr. Yen.